Hey everyone, and welcome back. So in the age of fancy AIs that can help us build complex machine learning models, almost automatically, you might think, do I even need to learn the details anymore? And the answer is of course yes. Because even with the best AI assistants, you are still the director. To get great results, there are two absolutely critical things you need to master. First, you need to know what to ask for. Which machine learning model is appropriate for your task? Like the decision tree we're covering today. How can you improve that model once you have a basic version? This means understanding concepts like tuning hyperparameters, the knobs and dials of the model, choosing the best features from your data, or even modifying existing ones to be more useful. Sometimes even modifying the target you're trying to predict. And finally, knowing how to save your best model and load it back up for use. Second, you need to understand your data. AI is powerful, but garbage in, garbage out still applies. You need to know how to check if your data is clean and makes sense, what to do when it's not perfect, how to effectively deal with missing data points or handle extreme examples. Outliers, that could throw off your model. While the specific techniques might vary slightly between datasets or different models, the fundamental principles of guiding the AI and ensuring data quality remain the same. And that's exactly what we're going to focus on today. We'll use the decision tree algorithm, a fundamental and interpretable model, and apply it to real-world tabular data, the popular Wisconsin breast cancer dataset. This will give us a concrete playground to practice both guiding the model building process and tackling common data preparation challenges. So if you want to learn how to effectively steer AI tools and build robust machine learning models by understanding these core concepts, you're in the right place. Let's dive in. We'll be working through a Jupyter notebook. You can download it from my site using the link in the description below. And now, first things first. We need a working Python environment. I recommend using Anaconda, which makes managing packages much easier. Once you have Anaconda installed, you can create a new environment with all the proper libraries and modules, and then launch Jupyter Notebook. Great, looks like we have the necessary tools installed and imported. So let's see a super simple example of a decision tree using Scikit-learn's built-in iris dataset. This dataset contains measurements of different iris flowers, and the goal is to classify them into species. And here we have it. So, what is a decision tree? Imagine a flowchart of questions, based on the answers to questions about the input data. The features: you follow branches down the tree until you reach a leaf node, which gives you the classification prediction. It's like a game of 20 questions the computer plays to categorize data. Now, a quick improvement. We trained and tested on the same data, which can lead to overfitting. The model memorizes the training data but doesn't generalize well. Let's split the data into a training set and a testing set. We use train test split. Random state ensures we get the same split every time we run the code. Now we train only on the training data. Let's check the scores. Score on the training data is 1.0. 100%. It learned the training data perfectly. Score on the unseen test data is slightly lower, around 97%. This is a more realistic measure of performance. Let's visualize this new tree, trained only on the training split. Notice the tree structure might be slightly different now because it was trained on less data. Okay, that was the basic idea. Now, let's tackle a more realistic and impactful problem. Classifying breast tumors as malignant, cancerous, or benign, non-cancerous, using the breast cancer Wisconsin dataset. Also available in Scikit-learn. This highlights how ML can be applied in areas like medical diagnostics. You can learn more about the dataset and how different algorithms perform with it from the dataset's website. And now we'll follow a more structured process like you would in a real project. We start with adapting our environment to that new problem. And after that, we can load the data. After loading the data, it's good to take a moment and understand what's inside. We need to figure out what our potential target is, the thing we want our model to predict. Then, we need to see what features are available, the inputs the model can learn from. Familiarizing ourselves with the dataset right at the start is a really important step in the process. Now, as we look at this data summary, you might think, can't I just paste this into my favorite AI and ask it to explain? And yes, you absolutely can use AI as a tool here. Ask it to summarize the key findings or point out potential issues. It's a good thinking, but also, and this is crucial, you still need to apply your own understanding. Read the AI's explanation. Then look back at the data. Does its summary make sense to you? Do you agree with its assessment? Does the data look correct based on that? If you're not sure, or if the AI missed something, don't hesitate, and ask it more specific questions until you're confident you understand the state of your data. Now, a crucial part of basic data analysis is checking for and handling missing data. As we can see, this particular dataset was prepared very cleanly. There's no missing data. That's great for us now, but it's important to remember that real-world data is often messy. So to make sure we know how to handle those situations, we'll actually simulate some missing data in a moment, and walk through the common techniques like dropping or filling the gaps. But before we mess up the data, let's just quickly check the data we do have using histograms, to get a better feel for the features. And now the missing data. First we remove the first value from the table, and we get not a number in a first cell, and we can see that in the same checks we made before. To deal with it, we can simply remove rows containing any missing values. Like we do here, the first row, index 0, is gone. This is easy, but you lose data. If you have many missing values scattered around, you could lose a significant portion of your dataset. You can also drop rows only if a specific column has a missing value. Or drop rows only if all values are missing. Less common. If a whole feature column has too many missing values or isn't very important, you might drop the entire column. Now, better. Often the best approach is to fill missing values. We replace nans with a calculated value, like the mean or median of that column. Let's add a few more nans for demonstration. Calculate the mean of each column, ignoring nans, and we can use fillna with the calculated means. The nans in rows 0, 1, and 2 can be replaced by the respective column means. Similarly, we can calculate the median and fill with the median. Median is often preferred if the data has outliers, as the mean can be skewed by extreme values. You can see how the mean, median filling affects these stats slightly, compared to the original data with nans. Of course, since our original has no missing data, we'll continue with that. But remember these techniques. Another data preparation step is checking for extreme values or outliers. These are data points significantly different from the rest, possibly due to errors or representing rare cases. They can sometimes negatively influence the model. Describe can give clues. Look at the min, max values compared to the 25th, 75th percentiles. IQR. Large differences might indicate outliers. For instance, mean area ranges from 143 to 2501. Is 2501 plausible or an error? Domain knowledge helps here. Histograms are great for visualizing distributions. This mean radius histogram looks reasonably distributed. Maybe slightly right skewed, but no single bar miles away from the others. Scatter matrices plot pairs of features against each other. This helps visualize relationships and potentially spot points far from the clusters. The colors represent the target classes: benign, malignant. Okay, so let's simulate an outlier now. Let's make the first mean radius extremely large, and look at the mean radius row now. The mean is much bigger, and the max is 1111.1. Clearly an outlier compared to the original max of approximately 28. The histogram confirms this, one tiny bar way out on the right. The scatter plots involving mean radius are now squashed because of the outlier's scale. So let's now try to handle this outlier. Similar to handling missing data, we can completely remove the outlier, and the plots will look good again. We can also replace it with the mean or median of the non-outlier data. And if you are not sure which method is the best in your situation, you can of course ask your favorite AI, like Gemini, Claude, or ChatGPT, to help you with that. But it's important for you to remember about this possible problem. Anyway, let's move further. Okay, let's intentionally modify our setup for a moment to see how choices impact the outcome. First, instead of all features, let's choose only 2 to predict our target: fractal dimension error and worst fractal dimension. Second, let's deliberately train our model on only a very small part of the data, say just 10%. Train size equals 0.1, leaving the other 90% for testing. Why are we doing this? This approach will clearly highlight how drastically feature selection and the amount of training data can influence the performance of our model. It sets us up perfectly to see the initial, perhaps weaker, result, and then understand how modifying these choices later will help us build a much better model. So, let's implement these changes now and see how the model performs. Just like before, let's train the model and check the score. 100% on training data. This is typical for a default decision tree that's allowed to grow deep. It perfectly memorizes the training set. Accuracy on the unseen test data is however much lower, around 60%. This gap between training and test score suggests overfitting, and probably tells us that the features we have and the amount of data is not enough for the great decision tree. Whoa, that's a complex tree, many levels deep. This visually confirms the overfitting. We can also check feature importance. As we can see, we only have 2 features, and they are both almost equally important. And if you want, you can check the predictions models give, and if they are correct, when the model predicts malignant, benign, and the actual class was malignant, benign, and when it wasn't. You can do these predictions for more than one item to see how the model performs. Okay, so we've clearly seen our basic, unrestricted tree overfits the training data. How can we fix this? A standard technique is hyperparameter tuning. Now, you could ask your favorite AI, how can I tune a decision tree to reduce overfitting? That's a valid way to get suggestions. These hyperparameters are essentially settings we choose before training the model. They act like control knobs. They definitely differ between various machine learning models, but we can always investigate them ourselves using Python's built-in help function on the model object, or, as mentioned, by asking an AI for an explanation of the parameters. The most important thing right now is for you to know that this concept, hyperparameter tuning, exists and is a critical step in building effective models. You need to know it's something you can and often should do. With that understanding, let's focus on a key hyperparameter for decision trees: max depth. This parameter directly limits how deep the tree can grow, which is a primary way to control its complexity and combat overfitting. So, let's modify max depth and see the impact. And look, the training score is no longer 100%, now around 82%. But the test score have improved from 60 to 70%. The gap between train and test scores is smaller, less overfitting. We can once again test it with different examples if we want. And now look at that tree. It is much simpler and interpretable. And the confusion matrix shows slightly different error patterns. Now, how do we find the best max depth or other hyperparameters? We can try several values and plot the results. We can create a for loop and let it do the hard work for us. This loop, for example, trains and tests a tree for each depth from 1 to 10. But you can decide how big the range of depth could be depending on the data you have. And you can either check all the confusion matrices to decide which parameter to choose, or you can plot all the accuracies in one place. And as you can see, the training accuracy keeps increasing with depth. Blue line. The test accuracy. Orange line. Increases initially. Peaks around depth 3 or 4. And then might slightly decrease or plateau. This peak is often the sweet spot between underfitting, too simple, and overfitting, too complex. That loop was manual. But Scikit-learn provides tools for automated hyperparameter searching as well. For example, GridSearchCV tries all combinations of parameters you specify. We tell it to search through max depth values 1 to 10. GridSearchCV uses cross-validation internally for more robust evaluation. It found that max depth equals 6 was the best in this range based on cross-validation. And this gives us the actual tree model trained with the best parameter found. Now, randomized search. It is useful when you have many hyperparameters. It samples random combinations instead of trying all, which can be faster. And it also found that max depth equals 6 was the best. Now, let's get back to feature selection. We do have 30 features here at the moment to use. But how many you think we'll use with max depth of 4? And as you can see, it seems like we used only 2 of them. As you probably remember, previously we've chosen fractal dimension error and worst fractal dimension just for fun. And now the model have chosen mean concave points and worst concavity, with mean concave points being much more important. Okay, we've talked about tweaking the model settings, the hyperparameters, and we've seen how changing the input features can make a difference. But there's another fundamental aspect you might modify, something really important to keep in mind as you design your machine learning solutions. And that's the target variable itself, the very thing you're actually asking the model to predict. Sometimes, depending on the exact question you need answered, or the specific decision you're trying to inform, you might redefine what outcome the model should aim for, even if you're using the same input data. A good example comes from the world of financial markets or trading. Imagine you have your set of input features, maybe current stock prices, trading volume, some technical indicators, maybe even news sentiment scores. That's your input data. Now, using that exact same input data, you could ask your model to predict several different targets. Will the price of the stock be higher in the next minute? Or, perhaps you're interested in a slightly longer time frame. Will the price be higher by the end of the next hour? Or maybe your strategy is daily. Will the price be higher by the close of the next trading day? See, each of those is a distinct prediction task, a different question, and because the goal is different, even though you're feeding it the same features, you would need to train a completely different decision tree, or whatever model you choose, specifically tailored and optimized for each of those different target outcomes, predicting the next minute, the next hour, or the next day. So, it's a powerful concept to remember. Defining your target clearly is crucial, and sometimes refining, or even changing that target, is a key part of building the most useful model for your specific needs. But that's a story for another day, and we'll stay with our target for now. Alright, let's try one more modification. Instead of changing the model's settings or features, let's change the amount of data we actually use to train it. Remember, we were using just a small 10% slice before. Now, let's use a more standard split, say, 75% for training. We'll keep the max depth fixed at 4, just like our previous best attempt. So we can really see how simply having more data impacts the outcome. So, we train the model again, and immediately you'll likely see better performance scores, especially on the test set. And take a look at the tree visualization now, compared to the tree built on only 10% of the data. This one, built on 75%, has changed quite a bit. It might be using different features or splitting points, because it had much more information to learn from. This really highlights how significantly the amount and quality of data can influence the final model. It's a fundamental principle in machine learning. And it's exactly like the big AI models we interact with, Gemini, Claude, ChatGPT. A major reason they're so powerful and knowledgeable is that they were trained on truly massive datasets. So, when you're working on your own projects, remember this: finding and preparing as much relevant, high-quality data as you reasonably can is often one of the most effective ways to potentially improve your model's performance. Now, we'll save our best model because we don't want to retrain it every time. First, we check if it's the one we want. And if so, Python's Pickle module lets us serialize Python objects, like our trained classifier, to a file. So that's what we'll do. And after that, our model is saved. And if we want, we can start a new session and use our pre-trained model. So let's restart our kernel now and run a minimal script that just loads the data for getting test examples and the saved model, and then asks the user for an item index to predict. And that's it. Now we can test our model however we want to see how it performs. We can even throw some curveballs to see how robust it is, and if it can handle wrong input. And this one sometimes can and sometimes can't. So you can ask your favorite AI to help you make it better if you want. And that's it. So we've covered a lot today, from the basics of decision trees with the iris dataset, to a more complex classification problem on the breast cancer dataset. We learned how to prepare data, handle missing values and outliers, split data, train a model, evaluate it, tune hyperparameters to avoid overfitting, visualize the results, and load our final model using Pickle. Now, if you want to play with other datasets, you can find a lot of useful ones in the internet. If you want to use other models, check my previous tutorials where I cover more than 50 different algorithms, from classification, simple and deep learning to reinforcement learning ones. And with that knowledge, you will be much better prepared to ask your favorite AI for help. You can tell it what exactly you want from your model, which steps you think it should take, and what to ask that AI about. I hope you liked this video and hopefully see you in the next one. And now, as they say, remember to subscribe to my YouTube channel, and hit that bell button to get the notification whenever I upload new video. You can also find the code from this testing in our AI and ML tutorial. More about me and my projects on my site, superai.pl. In the meantime, I wish you all the best in learning how to navigate this new world, where AIs can do so many amazing things. See you soon, and remember, improve yourself, improve your business, improve the world, but also live and have fun. Yours, SuperAI.